Welcome back to Chapter 22, uh, two sample proportions and inferences. Um, this is the second of maybe 3 or 4 videos on Chapter 22. So again, I left you off here on my first example, where we will be making a confidence interval given this situation. So here's the situation. At a community hospital, the burn center is experimenting with a new plasma compress treatment. A random sample of 316 patients with minor burns received the plasma compress treatment. Of these patients, it was found that 259 had no visible scars after treatment. So again, think about all that as one situation going on. So 259 out of 316. Okay, another random sample of 419 patients with minor burns received no plasma compress treatment. For this group, it was found that 94 had no visible scars after treatment. What is a 95% confidence interval of the difference in proportion of people who had no visible scars between the plasma compress treatment and control group? So again, think of those as two different things. So we had 94 out of 419, and we had 259 out of 316. We'll be coming back to those numbers in just a minute. So, state the parameter. P1 is the true proportion of patients who had no visible scars with the plasma compress treatment. P2 is the true proportion of patients who had no visible scars without the plasma compress treatment. So again, remember what the first one was with, and the second was without. That's why we write them that way. The difference, okay, so P1 minus P2, the true difference in proportion of patients who had no visible scars between the two treatments is P1 minus P2. So before we go ahead and start doing the math, remember step 2 was to go through our assumptions. So we have to go through and state them and justify them. So the treatments were assigned randomly to individuals, which is stated in the problem. So randomization, check. Both samples should be large. So let's go through our NPs and NQs. So our first one, remember the 259 out of 316? So there's my P times N. That gives us 259, which is definitely greater than 10. And Q, N1, Q1, so there's that 259 divided by 316 again. And again, you're doing the complement of that, and then timesing that by N. That gives us 57. Again, greater than 10. So that's our first true proportion. Now we're going to go through the second one. And again, these are to check to see if our samples are large enough. Now, the second situation that we had was with those people without the plasma compress treatment. The p-value in this one was 94 out of 419 times the 419, which is n. That got us 94, which is definitely greater than 10. Well, greater than equal to 10. And likewise, n times q, or n2 times q2, is our complement of p times n, and that gets us 325. So when all 4 of these are greater than or equal to 10, so therefore our samples are large enough. 3. The samples should be less than 10% of the population. So how do we figure that out? The population should be at least 7,350. Well, where'd that number come from? You take the 316 and you add that to 419. That's P1 plus P2. You get 735. Since it's 10% of that, you take 735 times 10. And that is the number that we have to be. So again, the population should be at least 7,350 burn patients. And again, we assume that. So, check, check, check. We have our 4. It is random. It is large enough. It is 10%. And that last one that's not written here is that independence. And hopefully you understand that the person or people who are receiving the plasma treatments is independent of one another receiving those treatments. So, since the conditions are met, a confidence interval for the difference of proportions is appropriate. So we're allowed to do that. So let's do that. We're going to calculate the confidence interval. Okay. So what do we know? We know the p-hat, or the probability of our first situation with n of our first, and the p-hat of our second situation and n of our second. Our confidence interval is 95%. So we're going to put all of this together into our formula. The formula again was given just a little while ago, and we're going to substitute into that. So here's P1, here's P2, there's our Z star, and this looks a little ugly again. All this is your P times Q divided by N. Here's your P times Q divided by N. And you have to do these separate because you're going to be adding them. And then you take the square root. Multiply that by 1.6 or 1.96. And that value is going to be added and subtracted to whatever the difference of these two fractions are. And once we do that, again, you're going to add that and subtract it. Our value for the confidence interval, for a 95% confidence interval, is 0.537 to 0.654. So here's our answer. So what do you do last? You explain the interval in the context of the problem. So again, go back to what the problem was talking about. Remember those plasma compress treatments? So we write our answer. We are 95% confident that the true difference in proportion of people who had no visible scars between plasma compress treatments and the control group is between 53.7% and 65.4%. Okay, so now that was if we were looking for our confidence interval. The other parts of this chapter talk about hypotheses tests. So let's go through that. The steps for a hypothesis test for the difference of two proportions is we define our parameter. You go through your hypothesis statements, your H sub O and H sub A. You have to go through your assumptions. You're going to do your calculations and find the p-value. You come up with your conclusion in the context of the problem. So again, it's similar to what we just were doing in chapter 20, 19, and 21. All right, so hypothesis statements. You have your null hypothesis. Now the way that, again, since there's two of them, we have to be very careful on how we write it. Your null hypothesis should be written in either one of these ways. you can write it as your first part, or your true parameter, true proportion of your first situation is equal to the true proportion of your second, or you can find the difference and set it equal to 0. Your alternative hypothesis, remember there's 3 different situations you can have. You can have P1 greater than P2, you can have P1 less than P2, and lastly, P1 not equal to P2. And just like before, the same rules apply. All right, now for our assumptions. The samples are chosen randomly and were chosen independently of each other. Or the treatments were assigned randomly to individuals or objects. And again, just like before, or vice versa. The samples both need to be large. So again, all 4 of these situations, NP or N1P1 and N1Q1, all both have to be greater than or equal to 10, as well as N2P2 and N2Q2, all again have to be greater than or equal to 10. And lastly, our 10% rule, again, both samples are less than 10% of the population. And don't forget about that independence and randomization. And once those conditions are met, we then move on to the actual test. Now, just like in our earlier chapters, we have a test statistic, and that's equal to this new thing that we haven't really had something written like this, but it may look familiar to you. We'll see. Here's your z equals. And this again may look familiar to you here if you think about it as y minus mu over standard deviation, maybe, our z-score. But again, because this is a hypothesis test of two of those proportions, we have to then think of it and do our differences of these things. So please be very careful on what you're doing here. Now, the subscript C, the book calls this pooling, and I'm going to talk in just a second about when the next little portion of my slide comes up of what this is here. So I'm going to pause the video and we'll come back in just a moment.